Hello everyone. Welcome back to another fascinating journey through the world of conic sections. Now, quick question. Have you ever watched a satellite orbiting the Earth or seen an athletics running track from above? Notice that shape? It's not a perfect circle. It's an ellipse. An ellipse is that elegant oval shape that nature absolutely loves. From planets moving around the sun to the path of a ball spinning off center. Mathematically, we define an ellipse as the locus of all points P such that the sum of their distances from two fixed points, called foci, is constant. That means, if the foci are f1 and f2, then for any point P on the ellipse, pf1 plus pf2 equals 2a. And this 2a is that magic constant that remains the same for every point. The line joining the two foci is called the major axis, and the one perpendicular to it through the center is the minor axis. The center is the midpoint of the foci, and the vertices lie at the ends of the major axis. So, if a circle is like the ellipse's chill cousin, both foci in the same spot, then the ellipse is the more dramatic sibling, stretching things out, but keeping balance beautifully. Alright, let's bring the ellipse into our coordinate plane. Imagine the ellipse is perfectly centered at the origin. That's point 0, 0. Place the foci at coordinates minus c, 0 and c, 0. Now for any point P, x, y on the ellipse, the sum of its distances from both foci is constant. Square root of bracket x plus c squared plus y squared close bracket plus square root of bracket x minus c squared plus y squared close bracket equals 2a. That's our starting equation. After some algebraic work, yes, a bit of squaring and simplifying, we arrive at the famous standard equation. X squared by squared plus y squared by b squared equals 1. And here's the special relationship between the parameters. B squared equals a squared minus c squared. That means as the foci move farther apart, the ellipse gets flatter because b becomes smaller. And if the foci come closer together, that means c tends to 0. And voila, the ellipse becomes a circle. So you can think of a circle as a zero eccentricity ellipse, the most relaxed version of an ellipse. Now, just like people, ellipses can face different directions, horizontally or vertically. If the major axis lies along the x-axis, we write x squared by squared plus y squared by b squared equals 1. If it's along the y-axis, the equation becomes x squared by b squared plus y squared by squared equals 1. In both cases, I is always greater than b. If you shift the ellipse from the origin to a new center, h, k, then the equation becomes x minus h squared by squared plus y minus k squared by b squared equals 1. And here's a cool condition for identifying an ellipse from a general quadratic. If the coefficients of x squared and y squared are positive and not equal, and b squared minus 4ac is less than 0, congratulations. You've got yourself an ellipse. It's like the math version of a personality test. If b squared minus 4ac is less than 0, you're definitely an ellipse. Now, let's talk about what makes ellipses truly magical, their focal properties. For any point P on the ellipse, the sum pf1 plus pf2 is always 2a, constant. That's the geometric soul of the ellipse. But here comes the showstopper, the reflective property. If you stand at one focus and whisper, your voice bounces off the ellipse and travels straight to the other focus. That's why places like the St. Paul's Cathedral Whispering Gallery and even elliptical auditoriums allow people to talk softly from opposite ends and still hear each other clearly. The same property makes ellipses useful in telescope mirrors, car headlights, and satellite dishes. The measure of how stretched an ellipse is called eccentricity, denoted by E. It's given by E equals c by a, where c is the focal distance and is the semi-major axis. For all ellipses, E lies between 0 and 1. Smaller e means more circular, larger e means more stretched. Let's now look at some important elements of the ellipse. Latus rectum. It's the chord that passes through the focus and is perpendicular to the major axis. For ellipse x squared by squared plus y squared by b squared equals 1, its length is to be squared by 8 directrices. These are the vertical lines x equals plus or minus or by e for any point P on the ellipse. The ratio PF by distance to the directrix equals E. This is what connects the ellipse definition to its algebraic form. You can express every point on an ellipse as x equals a cos t and y equals b sin t, where t is the eccentric angle. That parameter t ranges from 0 to 2 pi and helps us trace the entire ellipse easily. It's like giving the ellipse GPS coordinates. You can find every point using just one parameter t. Now let's quickly see how we can derive the standard ellipse equation directly from the focal definition. Start again with the rule. PF1 plus PF2 equals to A. That means square root of bracket x plus c squared plus y squared plus square root of bracket x minus c squared plus y squared equals to A. Isolate one of the square roots, square both sides, simplify, and square again to eliminate all radicals. After all the algebraic dust settles, you'll finally arrive at x squared by squared plus y squared by b squared equals 1, where b squared equals a squared minus c squared. Now test it. If x equals a, y equals 0, it satisfies perfectly. If x equals 0, y equals b also satisfies it. See, the math behaves beautifully when handled patiently, like a cat that actually comes when called. Alright, time to bring our ellipse journey full circle. Well, almost circle. Applications. Ellipses describe planetary orbits. According to Kepler's laws, planets move in elliptical paths with the sun at one focus. They're also used in optical designs, architecture, and even in statistics for confidence regions. Common mistakes. Swapping A and B when identifying axes. Using wrong signs for C or E. Forgetting that eccentricity must always be less than 1. Verification tips. Always check that b squared equals a squared minus c squared and E equals c by a. Substitute vertex A, 0 and covertex 0, b into the equation. Both must satisfy it. So, what did we learn? An ellipse is nature's perfect balance, part circle, part stretch, but fully symmetric. It's where geometry, physics, and beauty meet in one equation. X squared by squared plus y squared by b squared equals 1. And that's the ellipse, the oval of the universe, connecting math to the motion of planets and the whisper of sound. In our next video, we'll step into its hyperactive cousin, the hyperbola, where distances differ instead of adding up. Until then, keep your focus steady, your curiosity alive, and remember, math curves, but never breaks.